Hello there and welcome to MV Tutors. I'm Tsulu and I'll be looking at question 1 with you. We're on the chemistry paper now that was recently written for your November exams. So without further ado, let us get right to it. Before I forget, please do not forget to like our videos and subscribe to our channel. Please also spread the word to those who are in grade 11 this year going to grade 12 next year in 2022. So that they have these resources to their disposal. And also for those who are planning on upgrading their matric marks, specifically physics and maths, please, this is the right channel for you. Okay, cool. So, one point one, let us get to it. Which formula shows the way in which atoms are bonded in a molecule but does not show all the bond lines? Okay, so basically, if you were to have a structural formula, you would show the lines. Let's say you have ethane, no? What am I saying? This is 3 carbons, okay? So it would be propane. Okay, so that would be the structural formula. But if you're going to show how it is bonded without using bonding lines, okay, so it would be CH3, CH2, CH3. This is what they're talking about. This would be the condensed structural formula, okay? This was just an example I was making. So the answer they are looking for there is D, condensed structural formula, okay? And then 1.2, which one of the following compounds has hydrogen bonds between its molecules? Okay, so if you have studied what kind of bonds or forces exist between your hydrocarbons or any other functional group, you would know that alcohols, okay, so basically alcohols and carboxylic acids are the ones that have hydrogen bonding. Okay, so let's have a look. A looks like an alkane, so no. And then B, we have an oxygen atom somewhere in the middle. This must be a ketone. Okay, and C as well. Okay, we have two oxygen atoms next to each other. I don't know what that would be. I haven't seen that in this course. And then D, well, we have an OH on the second carbon. Okay, so it would look like this. So we have the first carbon. I'm going to draw the structural formula. And then we have the second carbon where you have a hydrogen. And then you have a OH group there. And then we have a third carbon with 2 hydrogens. By the way, this is the condensed structural formula. And then finally we have, so this would be butane 2-ol. Okay, 4 carbon atoms, butane, and then the OH is on the second carbon. So this is definitely the answer that we are going with, D. Okay, even this one was D. Okay, cool. And then 1.3, consider the compound below. All right, so let me just take it a bit up. Without even looking at the options given to us, let us name this compound and then go look for the name and the options. Okay, so we have 1, 2, I'm counting from the left, 1, 2, 3, 4, 5 carbons. Okay, so on the second carbon, if I'm counting from the left, I have a methyl group. Okay, and then the side 1, 2, 3, well, that's where I have my double bond to oxygen. So I have a ketone here. So which one do I start with? Do I start with the methyl group, which is on the second carbon, or do I start with the on the third carbon there? I would go with the methyl group on the second carbon. Okay, so how many carbons do I have in total? 1, 2, 3, 4, 5. So I have pent something. So it would be 2 methyl. Okay, so 2 methyl, and then I have, this is a ketone, so this is a 2 methyl pent 2-methyl pent 2, no, pent 3. It's on the third carbon. So pent 3-one. Okay, and do we have something like that? Oh, pentanon. Oh my gosh, I wrote pentone. Penton. My goodness. Okay, so penton 3-one. So a ketone, we see it there with the "one" there at the end, and we have 5 carbons, so pent. All right, and under the second carbon, we have a methyl group. So yes, you could have said 2-methyl 3-pentanone, however you want to pronounce it. Okay, so our answers there, well, that would be A. You wouldn't want to start counting this side and say 1, 2, 3, 4, meaning your methyl group is on the 4th carbon. You want it like to the closest side, so B wouldn't work out. And 2,3 dimethyl, no. And oh no, I don't want to even bother reading that one, so it will be A. Okay, we are going with A. Okay, and then let's go to 1.4. Go to the next page. Okay. Alrighty, so 1.4. A 2-gram piece of magnesium reacts with excess hydrochloric acid according to the following balanced equation. Okay, so you have a solid magnesium piece, and you have hydrochloric acid, which is in excess. Then you have the magnesium chloride, salt, and hydrogen gas. Okay, so now which one of the following changes will increase the yield of hydrogen? Okay, so if you want to increase the yield of hydrogen, you would have to increase your reactants. Okay, so if you increase any of your reactants, then according to Le Chatelier, it would be product favored, so you would get an increase in hydrogen in this case. What you would do as well, if you kept taking out the hydrogen, so if you kept removing the hydrogen, you removed some of the products, then again, according to Le Chatelier, it would shift to the product side. It would be product favored, okay, or forward reaction favored, so you can increase that. Okay, but let us read the options that we have. So A, crush the piece of magnesium. Okay, crushing it will turn it into powder, right? Meaning a higher surface area, but that is just increasing the rate of the reaction, not the yield. Okay, use a 3-gram piece of magnesium. Okay, so now we have a higher quantity of magnesium. So I can almost hear some of you saying, well, that won't make a difference because it's a solid. Well, we're not looking at what do you call this, chemical equilibrium at this point. We're just talking about the yield. So yes, you will consider this as one of the options. Okay, if you say use a greater volume of the acid, so if you use a greater volume of the acid, remember this acid is in excess, so it won't really make much of a difference. Okay, volume comes into play again when you're looking at chemical equilibrium, and maybe the equilibrium has shifted in some way. Okay, and then D, use a higher concentration of the acid. Same thing here, higher concentration. This hydrochloric acid is in excess. Okay, so I would assume that the magnesium is the limiting reactant. If magnesium ends, guys, it doesn't matter how much of the hydrochloric acid you have, it is in excess, it won't make a difference. So the winner here would be B. Okay, because you have a 3-gram piece of magnesium more than the 2-gram that you had initially. So like I said, increasing any of your reactants, your reaction will be product favored, and you will have a higher yield of hydrogen. Alrighty, and then 1.5, the Maxwell-Boltzmann distribution curve P represents the number of molecules against the kinetic energy of a certain reaction. So you guys know this graph, right? This should be very familiar. So if P is your original and Q is what you obtained after a change was made, okay? So we can see here the activation energy hasn't moved, okay? It's still the same, all right? So if you add a catalyst, what will that do? That will reduce your activation energy. So it will shift to the left. Okay, so activation energy would be, it would come in to the left of what we have currently. So that's not what we're seeing here. Okay, increase in temperature. So when you increase the temperature, your graph will be, how do I call it? It will be narrower. Okay, so under the graph, you still have the same number of molecules if you increase temperature. Okay, so, but again, the activation energy would change, sort of. So increasing the temperature, you have the same amount of the number of molecules, all right? But now you would have more molecules that are under, well, just after the activation energy. I think let me just draw this because I don't know if you're following me. Okay, so this is your original. This is P. Okay, so with P, we have our, let's say, our activation energies here. Okay, if you were to add a catalyst, no, actually, sorry. Let me make it a bit wider. Okay, so let me just do this. Okay, just for illustration purposes. And then I would say our activation energies here. Okay, so if you were to add a catalyst, your activation energy moves to the left. That's what I mean. It becomes less, right? Meaning more of your particles can actually have enough energy to have effective collisions. Okay, so that is the effect of a catalyst. Now, if I told you that underneath here we have like 1,000,000 particles, okay, if you are going to increase the temperature, your graph will do something like this. Okay, it'll be much thinner, but you still have the same amount of particles underneath. But if we look at our graph here, Q, there aren't the same. There aren't the same number of particles. We did not increase temperature in this case. Okay, so this would be like for temperature. All right, and then increase in activation energy. As you can see, the activation energy really stayed where it was. Okay, but D, increase in the concentration of reactants. So when you increase the concentration of reactants, you are increasing the number of molecules. And we can see the molecules here increased. And we can see that on the right-hand side of the activation energy, it's a bigger area, meaning more molecules actually have enough energy to form effective collisions. Okay, so this is the graph that would show us an increase in concentration. Okay, so that would be D. Alrighty, and then moving on now to 1.6. Alrighty. So yeah, the expression for the equilibrium constant of a hypothetical reaction is given as follows. So we have Kc is equal to x cubed, or the concentration of x to the power 3, y, and then on the denominator you have y, concentration of y to the power 2, and z. All right, so now it says, which one of the following equations for a reaction at equilibrium matches the above expression? Okay, let's just have a look at the expression. Okay, so we know that on the numerator we have products, on the denominator we have reactants. So let me just write it down. And the power that you would have represents the number of moles. So you would have 2y plus z as part of your reactants, and then you would have 3x. So we're going to look for this in the answers, okay? Another thing, remember in the Kc formula, you can only use aqueous solutions or gases. Okay, if you have solids or liquids, they do not go there because their value is like 1. So let us have a look. So part of our reactants, we have Z, so all of them have Z. Then we have 2y. Okay, so I would have gone with A, but the problem is I have a solid there by X, so that can't be. And then so again I have Z. I'm going to go with Z and 2y. Sorry about that. So Z, 2y, I I have 3x, great, and then I have Q as a solid, and Q was not featured in the Kc formula, so I would definitely go with D on this one. Okay, 1.6. 1.6 is D. Alrighty, and then 1.7. Okay, hope it's clear on your side. So it says 2 dilute acids of equal concentrations are added to separate test tubes shown below. 2 dilute acids. If it's dilute, it means it has a high concentration of water. Okay, cool. But anyway, we have 100 cubic centimeters of hydrochloric acid and we have 100 cubic centimeters of ethanoic acid. Yes, 2 C's, Cu. Remember Cu for carboxylic acid. So we know that the carboxylic acid there is a weak acid. Okay, normally organic compounds or organic acids are normally weaker. Hydrochloric acid is very strong. So now it says, consider the following statements regarding these acids. Okay, the pH of each is less than 7. Yes, they're both acids. So yes, that is true. Okay, so 1. Yeah, I'll put it like that. I would say it's true. And then let's look at 2 and 3. Okay, both will react at the same rate with 5 grams of magnesium powder. No. Because the strong acid dissociates completely, it'll have a higher reaction rate. Okay, the weak acid does not. I don't even want to say dissociate, ionize. You know, acids, they ionize, bases, they dissociate. But if you look at the dictionary, you'll get the same meaning for both ionization and dissociation. But anyway, so both of them actually, the stronger one, which is hydrochloric acid, that one will ionize completely. So it'll have a higher reaction rate. But your ethanoic acid will ionize incompletely. It will not ionize completely, okay? So its reaction rate will be lower. So no, I don't agree with statement number 2. 3, both will neutralize with the same number of moles of sodium hydroxide. No. Guys, remember when you are doing a titration, so if you have an acid and you're busy adding a base, so here we have a strong acid. Okay, so it depends. Are you titrating it with the, oh, this is a strong base. So sodium hydroxide is a strong base. So if you're going to titrate a strong base, or rather titrate a strong acid with a strong base, it will neutralize, okay? Your pH will be 7. But if you're going to take a weak acid and titrate it with a strong base, you're going to get a pH that is higher than 7. Okay, so it won't neutralize with the same number of moles. I don't agree. So statement number 3, I also do not agree with. So let's have a look at our options. And I would go with A because it's one only. B, definitely not. C, yeah, so we're only going with A. Alrighty, and then let's go to 1.8. Okay, another page. Okay, this is the last. We're left with 3 questions, guys. Then we're there. Question 1. Alright, you know, when I was in grade 10, when I was first introduced to the multiple choice, I honestly struggled because every option looked the same. And that's when I learned now that I can't cram anymore. I need to understand what it is that I'm studying. So understanding makes things much better and not cramming theory. All right, 1.8. Which one of the following is the conjugate base of H2PO4? Okay, so that is our acid there, ne? I know H3PO4 is phosphoric acid. I forgot what H2PO4 is. Anyway, this is our acid. It's a strong acid, okay? If you were to get a conjugate base of it, remember, according to the Lowry-Bronsted theorem, an acid is one that donates an H proton. Okay, so once it donates it, on the other side, it will be HPO4. But because we took a positive away, we're going to have a negative. Okay, if it was like H3PO4, then it would be a plus. No, forget that. We took away a hydrogen, we took away a positive, so now the net ion would be negative, okay? So that would be your acid. and that would be a conjugate base. So let's look for that answer. And in our options there, we have H. Wait. Oh, okay, guys. Sorry. There's a negative there. Yeah, because originally you have H3PO4. And then if you take away the H, you have H2PO4 minus. And if you take away another H, you have HPO4 2 minus. Or minus 2, however way they write it. Okay, I didn't see the minus there. This was not so clear. Sorry about that, but I should know from experience. So this is our conjugate base. So we're looking for H, PO4 2 minus, and that would be B. Okay, I'm gonna put it there. And then we are getting to 1.9. Okay, shift up the screen. Okay, 1.9. The diagram below represents a voltaic cell or a galvanic cell. Okay, so you have zinc on one side as a solid and copper. Okay, so just before we even answer this, I just wanted to explain again what happens in a voltaic cell. All right, so you initially have your zinc, right? And you have your copper. They're both solids. Those are your electrolytes, and you put them in. No, those are your electrodes that you're gonna put into the electrolyte solution. All right, and then once you have the salt bridge there, the salt bridge assists in making sure that there's an electrical current circulating between the two beakers. Okay, so now as that happens, so initially, another function of the salt bridge is to neutralize. Okay, so initially both of them are neutral, so both beakers are neutral. If you were to get a charge there, it'll be 0. It's neutral. So once you start connecting the voltmeter there and there's electricity flowing, there's a current flowing through the assistance of electrons. Remember, the anode side, that's where oxidation occurs. Oxidation is the loss of electrons. So electrons are busy going out from zinc, coming into copper, the copper electrode. So as that happens, zinc becomes skinnier, or rather it loses mass, okay? And then copper becomes, it gains mass. And as a result, you're gonna have a lot of zinc ions in that beaker over there. So remember, zinc has a charge of 2+, okay? And on this side, when the copper solid is busy getting bigger in mass, you're gonna have a lot of SO4 2 minus. Remember, the charge of a sulfate is 2 minus. So now the charge is not neutral anymore, okay? You have one beaker where zinc is, where you have excess zinc ions, so it's more positive. Then you have another beaker where you have an excess of sulfate ions, where now it's negative. So there's a charge, and that will influence the reading on the voltmeter, okay? It will actually eventually get to 0. So now what happens is the salt bridge is like, we need to get back to neutral, all right? So it will then release. So we said by the zinc, that's where you have your anode, right? And we said the anode, the beaker there with this anode, you have excess zinc ions. Okay, so it is highly positive. And then at the cathode, the beaker there has excess sulfate ions. So that is like negative. So what the salt bridge does, it's like, no guys, we need to get back to neutral. Okay, so that we can get a proper reading on the voltmeter. All right, so what happens is now, remember in the salt bridge, you have potassium ions and you also have chloride ions. So the chloride ion is like, whoa, I want to neutralize, so I'm going to go over there and balance the zinc out. And the potassium is like, okay, I'm also going to do my thing. I'm going to go to the beaker where it is excessively negative, and I'm going to come and I'm going to balance it. Okay, so that is what happens. Okay, so now let's see. Let's choose. It says, which one of the following correctly describes the movement of ions in the cell? Okay, so yeah, so X, this would be X, where this would represent X with the chlorine, and that would represent Y with the potassium. Okay, so now it says Y to X, ne? So the type of ions, okay, so which one goes from Y to X? The one that goes from Y to X, okay, no, never mind. You know what I did here? Okay, the direction. So in the whole salt bridge, you have all these ions, okay? Potassium and chloride and potassium and chloride, potassium and chloride. They are filled in the bridge, okay, in the salt bridge. So now what is going to move from Y to X? What's going to move from Y to X will be the chloride ions. What would move from X to Y would be the potassium ions. So let's go see. So A, Y to X chloride, yes. B, X to Y, no. That would be the potassium. C, Y to X, D, Y to X, no. So our answer there will be A. Okay, I hope I did not confuse you, and I hope that you are understanding what I did. All right, so we are nearly there, guys. Nearly there. We're there. Ne? So now we have 1.10. Okay, so 1.10. The diagram below represents a cell that is used for the refining of copper. You can see that we have an electrochemical cell where we have electric energy turning into chemical energy. Okay, so now which one of the following statements is true? Okay, before we even look at the statements, so here where X is, okay, let me just redraw it. I wanted to make notes on the actual image, but it will shrink, and yeah, I don't want to limit your visibility there. Okay, so you have your power supply. Okay, so this is your impure copper. All right, so if you have your impure copper, you want to electroplate it as this, refining, you want to refine. So if you have your impure copper here, what you would want to do once this chemical process starts, because of the electrical energy making things happen, okay, so whatever is impure here will settle to the bottom and form like a sludge kind of thing. Okay, and then the pure copper will actually go all the way this side and will make this one bigger in size, while this one actually shrinks. Okay, let me show this. I'll do copper with red, so it will actually come around here, which would be the pure copper, and then this side, well, you have less mass. It lost weight. Okay, so the one that's losing, so this side will definitely be your anode. Okay, all right, so this is actually going in this direction. So electrons are going from right to left. Okay, so these are your electrons there. So here, oxidation, that's where it happens. And on this side, you have your cathode, right? And that's where reduction occurs, okay, because electrons are coming in. All right, so yeah, that's basically what happens. Now, what is it saying? So this would be X, okay, where the pure copper is going to surround, and that's just the impure copper. So X is made of platinum. Is it? I don't think so. The mass of X increases. Yes, it definitely does. X is the electrode where oxidation takes place. No, that's where reduction takes place. X is connected to the positive terminal. No. So with an electrochemical cell, you have your positive this side. So I actually sketched this wrong because we're so used to the anode being on the left-hand side. So this is how it should be. So this is the positive and that's the negative side. So X is connected to the positive terminal. No. So basically our answer then would be B. Okay, and then that's where you're gonna get your pure copper. Okay, so yeah, we're done with question 10. And like I had said, guys, please don't forget to subscribe to our channel, spread the word with those who will be doing matric next year and those who will be upgrading, and don't forget to like our videos as well. Thank you. Hello everyone and welcome to MV Tutors. I'm Solo and I'll be looking at question 2 with you guys. Please don't forget to like our videos and subscribe to our channel, and please share the word with those who will be in matric next year, those upgrading as well. Okay, so don't keep this valuable information to yourself. Okay, question 2. So letters A to H in the table below represent 8 organic compounds. Okay, so we're just gonna have a look at that before we answer questions. What do we have there at A? We have carboxylic acid. Okay, so we see with the Q there at the end, and since it is 2 carbon atoms, that would be ethanoic acid. Okay, and then for B, what do we have? All right, so I see we have 1, 2, 3, 4, or 1, 2, 3, 4. Okay, fine. So we definitely have an alkene. Okay, and the second carbon, we have a methyl group. Okay, so yeah, 1, 2. So it will be 2 methyl. All right, I know this takes up some time, but it actually helps just to see what's going on and then answer the questions. So we have 2 methyl butene. Yes, 2 methyl bute, and on the second carbon again but2 ene. Okay, and then C, we have, all right, we have a condensed structural formula. So we have CH3, CH2, CH2, CO. So this is like a ketone. All right, and CH3. So this ketone, we have 1, 2, 3, 4, 5. So it is pentan. What does it fly? Pentan. So on which side? First carbon, second carbon. So it's pentan 2 one. Okay. D, let's just continue writing here. We have C2H6O. Sorry guys. C2, okay, and then H6, and then we have an O. How would this look if I were to just draw a structural formula just to see what's happening here? Like, do we have an alcohol? You know what's going on? What I can see though, maybe we have a double bond because we have 1, 2, 3, 4, 5, 6. Nope, not a double bond. So we have an alcohol. Okay, so we have 3, 6 H's, 2 carbons, 1 O. It's an alcohol and it's 2 carbons, so it would be ethanol. Okay. And then E, whew, we're only halfway. Okay, C2H4, that looks like an alkene. Okay, so that would be ethene. Okay, why did I all of a sudden use small letters? So ethene and ethanol. Okay, and then F. All right, there we have 3 methyl butane 2 one. Okay, so we have 4 carbons, 2, 3, 4, and on the third carbon we have a methyl group. Just gonna say CH3, and then on the second carbon, that's where you have your double bond to oxygen, and life continues for the others. Okay, if I just draw lines, I'm not gonna draw the hydrogen atoms, guys. It's gonna take forever. Okay, so yeah, 3 methyl, yes, and butane 2 one. Okay, cool. And then G, I'm just gonna put it up here. All right, so we have 1, 2, 3, 4, 5, 6. So we have hex something. On the second carbon, we have chlorine. On the third carbon, we have a methyl group. On the second, third, fourth, fifth carbon, we also have chlorine. So chlorine versus a methyl group. Which one are we going to start with? Well, alphabetically, chlorine comes first. So I would say 2. Let's see, 1, 2, 3, 4, 5, or 1, 2, 3. Either way, whichever way you start. So you have 2,5 dichloro, and then you have 3. I'm not going to go from the right to the left because now my methyl group is on carbon 4. So I'm going to go from the left to the right. So 2,5 dichloro, 3 methyl. There's also a line there. Oh, there's no space. 3 methyl hexane. Yes, 3 methyl hexane. This is it is saturated. It is a saturated compound. So I'm gonna go with 3 methyl hexane. All right, and then H. Well, we have 3 methyl butanol. Okay, butanol meaning it is an aldehyde. An aldehyde is a functional isomer of the ketone. Okay, so again we have 4 carbon atoms, and on the third one we have a methyl group. Okay, and it is a 3 methyl butanol. So I would say on the first carbon, that's where you have your double bond to oxygen. Okay, and we are done with just looking what's at the table. Now let's answer questions, guys. I hope us doing that exercise will help us answer questions like quick, chop. Okay, so now define the term unsaturated compound. Okay, so an unsaturated compound is a compound that has double bonds, triple bonds. I haven't seen one that has 4 bonds actually in the organic chemistry. I haven't. So unsaturated compound, a compound or a hydrocarbon that has should be writing this. I'm just gonna say double or triple bonds. Okay, I've been talking, so you know. Basically, if it is unsaturated, it means that it can be broken down. You can add more to it. That is why with saturated compounds, you can't have addition reactions, only elimination and substitution. But with unsaturated, you can definitely add on. All right. So yes. And then 2.2.1, letter that represents an unsaturated compound. So we're gonna go have a look. Which one here is unsaturated? Well, I see ene for B. Okay, so alkenes, alkynes, unsaturated. So I see ene here, and I also see ene there for E. So B and E. B or E. It's only one mark, so it's up to you. You could either say B or E. Yeah. Okay, 2.2.2. Name of the functional group of compound C. So say it's C. It is a, what am I doing now? So C is a ketone. Okay, so that is the functional group. Yes, homologous series. So I would say it is a ketone. A ketone has a double bond to oxygen somewhere in between. But if it has a double bond to oxygen at the ends, that would be an aldehyde. Okay. And then 2.2.3, letter that represents a chain isomer of compound C. Okay, so if it's a chain isomer, you just moved something somewhere. Okay, it's nothing hectic. Functional groups did not change. It's just a matter of something moved. Okay, so let's have a look at C. So C, we said it's pentan 2-one. Okay, so we're gonna have to look for some pentan again somewhere, or maybe another ketone. Okay, wait. Chain isomer of compound C. C, how many C's were there? 1, 2, 3, 4, 5. Okay, now I'm making sure. F. Where's F? We have 1, 2, 3, 4, 5. We have 5 carbon atoms. Okay. How many hydrogens do we have? We have 3, 4, 5, 6, 7. We have 10. And then C has 3, 3, 4, 4. So it's also 10. So I would believe, because I have a ketone for C and I have a ketone for F as well, right? F, yes, yes. So yeah, that should be the chain isomer. So for C, it would be F. Okay, and then 2, 2, 4. The IUPAC name for compound G. Ah, we wrote it down, didn't we? So you just copy this. 2, 5, dichloro. 2, 5, dichloro. And I think on the third, yes, 3 methyl. Now we actually have space. So 2, 5 dichloro, 3 methyl hexane. Okay, things are going well so far. We are actually moving. General formula of the homologous series to which compound E belongs. So C2H4, we said that that is ethene. Okay, so that belongs to the alkenes. Oh, but they want the general formula. Okay, so the general formula, you have CN, so that would be H2N, because you see H is like double that of C. All right, and then we come to 2, 3. Okay, 2, 3. Right, define the term. Jeez, we still have a long way to go. Define the term functional isomers. So functional isomers, guys, they have the same molecular formula. Okay, if you write down the molecular formula, it's there, but they belong to different homologous series or different functional groups. And the two that I can tell you about that I know, you have you actually have carboxylic acids. They're actually functional isomers to, I almost said ethanoates, to esters, okay? And we have, like I've been saying, ketones that are functional isomers of aldehydes. Those are the two functional isomers that I'm aware of. All right, and then 2, 4, they didn't ask us, okay, I'm going overboard. They didn't ask us for examples. They just wanted the definition. I was just going a little bit extra. For compound A, write down the homologous series to which it belongs. Okay, so 2, 4, 1, homologous series. Oh, for compound A, what did we say for A? A is the ethanoic acid. Okay, so ethanoic acid, it belongs to the carboxylic acid. Carboxylic acid. Okay, and then 2, 4, 2, for compound A, write down the structural formula of its functional isomer. Okay, so whenever you form an ester, you actually need an alcohol, okay, and a carboxylic acid. And your product would be an ester and water. Okay, so now they want the structural formula of its functional isomer. It was ethanoic acid. Now, so it just has 2 carbons there, so it's not a bad one. So we have an alcohol here. So we have methane, okay, and we have the OH group. And we have the carboxylic acid, so that would be methanoic acid. Okay, so what you do there, you take out water, H2O, and whatever's remaining, you plug it together, because I'm going to put that in green. So the structural formula for the functional isomer, you have C connected to H. I'm going to put everything now because they requested for a structural formula. And then we have a O. Okay, and then we have another C and a double bond to O and another bond to hydrogen. Okay, I actually forgot a hydrogen there. You must always make sure that whatever is surrounding your carbon, it's only 4 elements, okay, not more than 4 or less, unless if you have a double bond. But yet the numbers, the lines must be 4. Okay, so this would be the structural formula. Okay, and if they wanted the name for it, it would be methyl methanoate. Okay, so you start with the alcohol, methyl methanoate. That would be your ester. It always ends with the O8. Okay, we are almost there, guys. So 2.5.1. Compound D undergoes a dehydration reaction. So we are taking out water. Okay, so dehydration reaction. Where is compound D? Ish, see now, things are far up there. So compound D is an alcohol. Okay, so we're gonna remove H2O. So this is ethanol. This thing is so sensitive. Okay, we're gonna remove, we have ethanol now. Let me just put the structural formula for it. So ethanol, I have a OH. Okay, so it undergoes dehydration reaction. And let's just say this is 2.5. So this is the structural formula for it. Okay, with the hydrogens. The correct way to actually draw a structural formula for an alcohol, you must make sure that the O and the H actually also have their own line, okay, bonding line. So this is ethanol, right? Now let's answer the question. So 2,5,1, the IUPAC name for compound D. Is this D that we're looking at? Yes, it is. Girl, what's happening? Okay, compound name, so that is ethanol. Okay, and then 2,5,2, let me just shift this up. Okay, so we have ethanol over there. Okay, so the letter that represents a product of this reaction. Okay, oh, the product. So I get it undergoes dehydration. Okay, so if it undergoes dehydration, remember we're removing water from it, because now if you are dehydrated, it means you really need water. Okay, so if you take that out, now you are left with what? Okay, there'll be a double bond, right? So you have H there. Yeah, maybe I just took too much from one carbon, but anyway, you have H there and you have H there. Okay, you're left with only 4 hydrogen atoms. Okay, and it's a double bond, so it's going to be something like this. So the letter that represents a product of this reaction, we had a theme somewhere, so that would be E. Okay, so yeah, the letter would be E. All right. Okay, and then name or formula of the inorganic reactant that is used in this reaction. So basically, if you're going to dehydrate it, what exactly assisted us in doing this dehydration reaction? Remember, this is like an elimination reaction. So what did we use? What catalyst, you know? Yeah, in this case, that would be sulfuric acid. I actually forgot if it's concentrated or diluted, but I think it's concentrated. Yes, concentrated sulfuric acid. Okay, but they just wanted the formula, so H2SO4 would be sufficient. And guys, we are done with question 2. Remember, yes, question 2. Remember guys, please spread the word, like our videos, subscribe to our channel. Bye. Hello everyone and welcome to MV Tutors. I'm Solo and I'll be looking at question 3 with you guys. I'm pretty much going to be doing hydrocarbons with you. I wanted to say organic reaction questions with you. So yes, I'll be handling the organic reaction questions as you've noticed, and also the electrochemical cells at the end. Okay, so let's do this. Don't forget to like our videos and subscribe to our channel and spread the word to those who'll be doing matric in 2022, either upgrading or those going from grade 11 to grade 12. Alrighty, so let's get to it. Question 3. The melting points and boiling points of 4 straight chain alkanes are shown in the table below. Alright, so we have pentane, hexane. So yeah, pentane, hexane, heptane, octane. Alright, so now define the term melting point. Okay, so loosely translated, I would say the melting point is when a solid turns into a liquid or the temperature that the solid starts turning into a liquid. But let us formalize it. So a melting point, okay, so it's important to mention that it's the temperature at which a solid and liquid phase liquid phases of a substance are at equilibrium. Okay, yeah, so solid and liquid phases of a substance are at equilibrium. I mean, that's the formal one, but I mean, in an exam situation, if I forget this formal one, I'm just going to think about it like, hey, is a temperature or a solid transforms and becomes a liquid. All right. Okay. Now write down a general conclusion that can be made about the melting points of straight alkane chains. So let's have a look. So when you have a pentane, you had a melting point of a negative 130. Okay. And then hexane, negative 94. Heptane. So the longer the chains become, okay, so that's what I'm just gonna write. So the longer the chains, okay, these chains obviously have a higher surface area, higher SA, not South Africa, higher surface area. So the longer the chains are, okay, the higher the melting point. So the longer the chains, the higher. Please don't be tempted to say the lower because you see a low number. There's a negative there. So the lower the chain, the longer the chains, meaning there's a higher surface area, the higher the melting point. Actually, melting point and boiling point go hand in hand. All right, so yeah, even here you can see the boiling point increases as you have a longer chain. Okay, so the longer the chains, the higher the melting point. That's what we can say. And then 3.3, okay, let me just take the screen a little bit higher. Okay, so now it says, name the type of van der Waals forces between the molecules of octane. Okay, so yeah, like at this point, octane has the highest melting point and also has the highest boiling point. Okay, but the van der Waals forces, so generally between hydrocarbons, you would have London forces. Okay, but if we put alcohol in the mix, remember alcohol and carboxylic acids, they have hydrogen bonding within them. So they're very strong bonds, okay, compared to London forces. So in this case, we would call them London forces. Sometimes you can go deeper, like, okay, what kind of London force? Is it dipole, or dipole induced? Or, yeah, we're not going there, okay? The marks don't allow us to elaborate that far. So let's just end it here. And then 3.4, write down the predominant phase of the following alkanes at negative 100 degrees Celsius. So choose from gas, liquid, or solid. Okay, if we have a look at pentane, Pentane is negative 100, okay, when it starts to melt. So from negative 130, sorry, negative 130. So negative 130, it's so, okay, let me put it this way. So at negative 130, it's going from a solid to a liquid, okay? And at boiling point, we have 36.1, right? At boiling point, we say we go from a liquid to a gas. There's a more formal definition for boiling point, a more, yeah, sophisticated one. But yes, so negative 100 degrees is somewhere here. And I mean, what is common here? We see that's where the liquid is, right? So I would say for pentane, liquid, right? And then 3.4.2 octane. Okay, so let's also let's do what we did previously. So here we go from solid to liquid, and then when we go from liquid to gas, we have 125 degrees Celsius, and we have negative 100 there. Negative 100 degrees. Okay, so let's see. It's melting at, ooh, yo, look at me and where I put this 100. 100 will definitely not be there, guys. 100 will be this side. Ish. Yes, 100 will be that side. So what's there? That would be the solid. Okay. I almost said what? It's a liquid again. Yeah, so octane is a solid at negative 100 degrees and pentane is a liquid. Okay. And that is why octane would have a higher melting point or a higher boiling point. Okay, it takes time because the forces are generally stronger with longer chains as compared to shorter chains. So it'll take quite a while before, you know, it melts or it boils. All right, now 3.5.1. So now they say hexane is now compared to 2,2 dimethyl butane. So let's see, how does that look? So we have 6 carbons, right, for hexane. Okay, I'm not going to put in the hydrogen atoms just for time's sake. But yes, but our thing would be 6 C6H14, right? Because with alkanes, the general formula will be CnH2n plus 2. Okay, so that is hexane. And we're comparing it to 2,2 dimethyl butane. So I'm going to put 4 carbon atoms. On the second carbon, we have a methyl group. Okay, we also have another methyl group. Okay, and then we have our hydrogens there. All right, so still we have 6 carbons, and you can go count. It's 3 on top, 6, 9, 12, 14. So molecular formula is the same. All right, so now let's answer the questions. What do they want? So now 3.5.1, let me just make that 3.5. And now 3.5.1. Is the molecular mass of hexane greater than, less than, or equal to that of the 2,2 dimethyl butane? Okay, guys, molecular mass, you have the same molecular formula. If you go look at your periodic table, C is like, it has a molar mass of 12, hydrogen a molar mass of 1. For both of them, you're going to have the same mass. Okay, so this is equal to. And why? Because you have the same molecular formula. Hence, or rather, therefore, same mass, molecular mass. Okay, and then now 3.5.2. Is the boiling point of 2,2 dimethyl butane higher than, lower than, or equal to that of hexane? So guys, when you have straight chains, okay, so straight chains generally have higher boiling point of branched chains. Okay, why is that? The straight chains have a higher surface area. Okay, these ones, it's a smaller surface area to cover that is exposed. Okay, so these ones, the branch chains have a lower surface area that is exposed, whereas straight chains have a higher surface area that is exposed, and therefore the straight chains will have a higher boiling point or melting point, and the branched chains will have a lower boiling point or melting point. So is the boiling point of 2,2 dimethyl butane higher? No, it's definitely going to be lower than. Oh, and we're pretty much done. So it will be lower than. Lower than is your answer. And 3,5,3, this. This is your explanation. We talked about it. And we are now, oh, how many marks? I can't see how many marks this was. But here's the thing. You're going to talk about the chain itself. First of all, you have a straight chain for hexane and you have a branch chain. Okay, because of the straight chain, you have a higher surface area, okay, that is exposed, and a branch chain has a lower surface area that is exposed. Okay, so as a result, the bond, so that you have stronger bonds for the straight chains. Okay, I think that's something that's you can mention as well. And for you to overcome or to break those bonds, you need higher energy. Whereas with branch chains, you don't really need that high energy to break the bonds. And because you need that high energy, end up having a high boiling point or melting point for straight chains. Okay, so I mentioned quite a few things. I think you should talk about energy as well. This is, you need a high energy to break the bonds. And as a result, that's where you then have a high boiling point and a high melting point. Okay, I don't know, I think maybe the marks would be like 3 or 4 or something. But yeah, that's pretty much it. I said all I think should be addressed. So we are done with question 3. This was actually, yeah, it flowed. So I hope that you guys are cool. Please don't forget to like our videos, subscribe to our channel, spread the word. Bye. Hello everyone and welcome to NB Tutors. I'm Tulu and I'm still with you guys with organic chemistry. And now we're going to look at organic reactions. Okay, question 4. So compound P is used as a starting reactant in each of the 2 reactions as shown in the flow diagram below. So we have compound P there. Okay, so we don't actually know the structure. I can see that this is a saturated compound. Why? Because I have 5 carbon atoms and I have 12 supporting atoms. Okay, so the general formula being CN, what is this, H2N plus 2, but actually because we have a because we have a halogen there, it becomes a haloalkane. But is it, it's a haloalkane, but how is the structure? Do we have something that is a straight chain? Do we have a branch chain? How do we know? So I'm going to just look as well. So if you go now to the right, reaction number 1, there's actually more information. So we have 2-methyl butane 1O. Let's just sketch that. So we have 2-methyl, so we have butane, we have butanol, we have an alcohol, right? So 1, 2, 3, 4. And on my second one, I have a methyl group. Okay, I'm going to just put it as CH3 so that I know it's a methyl group. And then on the first carbon, I have my alcohol. Okay. Okay, let me just put it together. Actually, you know what? Let me make this my 4th carbon. And let's just do this rather. So 1, 2, okay. I'm going to make this 1 and that 2, that 3 and that 4. So on the first carbon, we have our OH group. I'm also going to keep it together. All right. And then we said on our second carbon, we have that methyl group. Okay, so that is 2-methyl-butane-1-ol. Okay, 4 carbons. And then the rest are just hydrogen atoms. Okay, cool. So this is what happens, right? This is our arrow there. I'm going to make the arrows black. And that is reaction 1. So now compound P, okay, it will not look that different from this 2-methyl-butanol, this alcohol. It won't look that different. So like I said, how do we know whether compound P is a straight chain or a branch chain? This piece of information actually gives us an idea. So we are going to have a branched chain. Okay, so we're still going to have 4 carbons. 1, 2, 3, 4. And on the second carbon, we're going to have that methyl group still. Okay, but somewhere we're going to have that bromine. Okay, that halogen. So where? I believe because alkanes or haloalkanes, they either undergo substitution or elimination. Here we've substituted. Okay, so I'm going to assume with confidence that on the first carbon we actually have that bromine atom. Okay, and then we have the supporting stuff, cast the hydrogens. Okay, and I need to make sure it is 11 hydrogens. So I have 3 this side, 4, 5, 6, 7, 8 plus 3, that's 11. I have bromine and I have 5 carbon atoms, so we are good to go. And this one, what would we call it? We would call it, remember, I'm starting from this side. Okay, so you have a bromo on 1 and you have a methyl on 2. So I would say 1 bromo, 2 methyl butane. Okay, it's a haloalkane. Okay, just wanna maybe write that. Haloalkane. All right. Yeah, 1 bromo, 2 methyl butane. And this one, they already gave us the name. We have 2 methyl butane 1-ol. Okay, so if I were to now see here, I have dilute sodium hydroxide. Okay, so what kind of a reaction? It would definitely, like I said, haloalkane, it either undergoes substitution or it undergoes elimination. If it were eliminated, you would have a double bond. Okay, so this is definitely a substitution reaction. Okay, so I'm just gonna write there, substitution. And another thing, whenever you see sodium hydroxide, whether it is dilute or it is concentrated, you know it's because you were dealing with a haloalkane. Okay, but yeah, so it is a substitution reaction. Okay, and what kind would it be? Well, this one, because we've replaced or substituted the bromine with the OH group. Remember, there's also plus here HBr. Okay, all right, so yeah, we have a HBr somewhere there. But yeah, so what kind of substitution reaction is this? I would say it is hydrolysis. You know, because of that sodium hydroxide, that dilute sodium hydroxide. If it's dilute, guys, it means there is a high concentration of water. All right, we have a lot of water poured into it. It makes sense if you dilute something, obviously it will be more watery. Okay, and now we get to reaction number 2. All right, and there we have concentrated sodium hydroxide. So this is diluted, and this one, it is concentrated. So Now we have compound Q. Okay, so if it is concentrated sodium hydroxide, compound Q, guys, if you really go through your reactions, you'll see that that is where we have dehydrohalogenation. You're actually dehydrating this thing. Okay, it's undergoing dehydrohalogenation because of that halogen there, that Br. If it was just a hydrocarbon without any halogen, then it would just be dehydration. Okay, so yes, so we are gonna take out from the dehydrated basically, and that will then become an elimination reaction. Okay, so there we have an elimination reaction for reaction number 2. Okay, and the type of elimination reaction D, so elimination reaction, and the type, so there we had hydrolysis. This one is going to be dehydrohalogenation. Okay, and what then do we have? Sorry, I know parts of it is going to be hidden, but you still have your 4 carbon atoms. Okay, you still gonna have your methyl group on the second one. Okay, but because we are eliminating, what are we eliminating? We are eliminating a hydrogen, and we are also eliminating a halogen, so you're gonna have a double bond over there. Okay, so just gonna have hydrogen there. Okay, now I'm putting the H's. I'm not being consistent, but yes, so there you have removed a hydrogen. You also have removed a bromine atom. Okay, and what are we left with here? What do we call this compound? Okay, so yeah, we don't have a halogen anymore. We've removed one of the hydrogens, so we have butene. Okay, so it will be 2-methyl but 1-ene. Okay, so that's what we have. And then after doing that, because now we have an alkene over here, now we're gonna add HBr, so hydrogen bromide. Okay, hydrogen bromine, bromic acid. So if we are now going to add it, so the type of reaction that we get on the third, it's actually an addition reaction. And what kind of an addition reaction? Well, it's a hydrohalogenation, because we're adding a hydrogen and we're also adding a halogen. So hydrohalogenation. All right, and what would be our major product? Okay, guys, so there are rules. There's a rule called the Markovnikov rule, where it says if you now break apart a double bond, what would happen? Where would the bromine go? Where would the hydrogen go? Okay, so again, we have our 4 carbon atoms. On the second one, we're still maintaining our methyl group. These ones, carbon 3 and number 4, they are not affected by what happens. Okay, but now because it's an addition reaction, this double bond breaks into a single bond. Now, where are you going to put that hydrogen, and where are you going to put that bromine atom? Well, I'm going to look at the carbon that has the most hydrogens, and that carbon that has the most hydrogens, that's where I'm going to put my bromine atom. Okay, so if I look here, this carbon here, it's attached to a carbon. Okay, it's attached to a methyl group, and then this one is also attached. Okay, so another thing, so the carbon that has the most hydrogen will be carbon number 1. Okay, but now if I put bromine on carbon number 1, I'm back to compound P. And I don't think we're trying to go back to compound P. We're trying to get a different compound. So then I would rather put the bromine atom where the second carbon is, and then I'll put the H atom where you have the most hydrogens. I'm going to put it at the carbon that has the most hydrogens. So my first carbon will just be surrounded by hydrogens, and then the second carbon will have the bromine there. Okay, so that's also like, yeah, so you can go and read about Markovnikov's rule, and it actually explains this quite well, especially if you're confused. What made this easy for me is, let me just zoom out a bit. What made this easy for me to see is that the first compound B, it had a bromine atom on the first carbon. So for me to go back and put it on the first carbon doesn't make sense. Okay, so we're going to put it on the second carbon. All right, so I think we are ready now to answer questions. We've taken time, but we are ready. Okay, so 4.1.1. Okay, name the type of reaction represented by 1. Well, we did say it is a substitution reaction. All right. Substitution reaction, if you want to go deeper, you can say hydrolysis reaction. Okay. So substitution reaction, hydrolysis. All right, so 4.1.2 is 2-methyl-butane-1-ol a primary, secondary, or tertiary alcohol? Okay, guys, if you have a look at it, did we draw the structural formula? Yes, we did. So how can you tell whether something is a primary, secondary, or tertiary alcohol, almost a third alcohol? Well, basically, you need to look at your OH group, now your hydroxyl group. The carbon that this hydroxyl group is attached to, how many other carbons is it attached to? Okay, so this is your OH group, ne? It's attached to this carbon number 1. Now, this carbon, how many other carbons is it attached to? It's only attached to 1 carbon. So because it's only attached to 1 carbon, it would be a primary alcohol. If maybe you had a methyl group here, then you see this carbon is now attached to 2 carbons. So it would be a secondary alcohol. If you had a methyl group over here, then this carbon is attached to 3 carbons. Then it would be a tertiary alcohol. So this is not what we have. We have a primary alcohol. Okay, so we can go back and write our answer. 4.1.2, primary alcohol. Okay, now give a reason for your answer. Well, basically, the carbon that the hydroxyl group is attached to is attached to 1 carbon, or has 1 neighboring carbon. But yeah, so the carbon that the OH group is attached to 1 carbon. I know, it's like, what are you saying? Well, yeah, so write down the structural formula for compound P. Okay, guys, we've already done it. We did it here. So you just take a copy of this structure here. Oh, but okay. No, let me do it proper. So the structural formula for compound P. Okay, I'm going to do it proper. So again, I have 4 carbon atoms. On the first carbon, I have the bromine. On the second carbon, I have the methyl group. So I need to then put the hydrogens there. Okay, hydrogen. So this is a proper structural formula. Okay, so that is the structural formula for compound P. And then name the type of reaction represented by 2. Well, that is a elimination reaction. Elimination reaction, and the type would be dehydrohallucination. Okay, you don't have to write the dehydrohallucination, you can just put the elimination reaction. Okay, I'm just giving extra information. And then it says, to which homologous series does compound Q belong? I think that was the alkene, ne? Yes, it is an alkene. Okay. Alkene, and then 4.1.6. Name the type of reaction represented by 3. Well, that is an addition reaction. Okay, the type hydro, because we have H, and then Br, halogenation. Okay, and oh, sorry, I didn't even read the second part. Choose from addition, elimination, substitution. Okay, fine, they just want addition. Ish. No, I had that habit of not reading the whole question. Some would say, papa, you're so forward. So I'm doing a little bit forward here. 4.1.7. Write down the IUPAC name for compound R. Did we end up writing that name? We left it, ne? We didn't write it. Okay, so let's write it here. So what is happening here? So you have your first carbon, okay, second carbon. So basically you have 2 bromo. Remember, bromo comes before methyl, alphabet wise. So 2 bromo, 2 methyl, 2 bromo, 2 methyl, 2 bromo, 2 methyl, butane. Ish. Am I gonna make it? Barely. But it's there. So 2 bromo, 2 methyl, butane. Okay, so that is the IUPAC name of compound R. Okay, so this is the first part of question 4. Let me just write it again. 2 bromo, because B comes before M. 2 methyl butane. Okay, and then now we go to 4.2. I'm gonna have to look for it. It was lost somewhere. Okay, this is not put well together. Okay, so 4.2, part of it has been cut off, but we can make it out for you. Okay, so 1,2 dibromopropane can be prepared from butene. Okay, so but they're telling us, so if you have butene, this is butene. Okay, butene can be used to prepare 1,2 dibromopropane. What? We first started with 4 carbons and now we just left with 3. What happened? Okay, so that's 1, 2, and that's 3. So it is 1,2 dibromo. So I have a bromine atom there and I have a bromine atom there. 1,2 dibromopropane. So it is a saturated compound. We started off with an unsaturated compound and now we're headed to a saturated compound with 2 bromine atoms. And it can be prepared by a 3-step process as shown in the flow diagram below. Okay, so this is what we're starting with. This is what we should be ending with. So what happened here? Okay, I'm going to try to draw this again. Let me just rub out what the answer would be. Okay. But basically, that's what we are ending up with. So what actually happened? Okay, you had butene, all right? And you underwent step 1. So what I would do, first and foremost, I want to break apart that double bond. I want to add to it. So step 1, it's an addition reaction. Why? Because I want to get rid of that double bond so that I can see clearly. And currently we have a hydrocarbon, so you need to tell yourself at the end, I need to end up with 2 bromine atoms. So what am I going to do? Am I going to add a hydrobromine or a bromic acid, or am I just going to add hydrogen? So yeah, here's the thing. Are you going to add HBr? Are you going to add H2? what will actually influence your decision. Okay, the fact that we have to go from 4 carbons to 3 carbons tells us that somewhere, somehow, there has to be cracking, because there is no reaction that I know of for this syllabus where you can go from having 4 carbons to 3 and the other one just disappears. I don't know any reaction that just breaks apart alkanes, okay, or any organic compound, okay. So for me, then it would make sense to have it to crack, okay. And cracking, I should actually check this out, but I've only seen cracking happen for alkanes. So you have an alkane, it cracks, and then it forms an alkane and an alkene. Okay, so I haven't seen a haloalkane cracking. I've only seen alkanes crack, or heard of. Okay, let me not say I've seen it, I've heard of. So basically, after step 1, I'm going to have butane. Okay, butane. So what does that mean? It means I added hydrogen atoms. Okay, so there I would have an addition reaction, and the type would be hydrogenation because I've added hydrogens. So hydrogenation. Okay, so I have my butane, that is step 1. Step 2, like I said, I can then crack it, okay, because I want to end up with I want to end up with three carbon atoms, a propane. Okay, that's part of the product that we want. So if I apply some cracking, I'm definitely gonna have an alkane. Remember, when we crack, your product will be an alkane and an alkene. Okay, so I'll have an alkane, which is methane. Okay, so I'll have methane, and then I will have propene. The nice thing about propene, you can either have the double bond this side or that side, doesn't matter. Okay, so I have with me here propene. Okay, so I have that's basically, it underwent cracking. So this is step 2. So this is step 1 over here, and this is step 2. Step 2, we had some cracking. What does cracking produce? It produces an alkane and an alkene. Okay, so that is step number 2. Now, okay, some things are going to be hidden, just bear with me. Step number 3. So step number 3, I have this compound B. Okay, so I then need to take this propene and then I need to add something to it, because my final product is not an alkene, it is an alkane. Okay, it is a haloalkane. So what am I gonna add to it to get a haloalkane? I will add a halogen. Okay, so I have an addition reaction here. Remember, addition reactions only apply to double bonds and triple bonds. So I have an addition reaction, and this one will be a halogenation, because I'm adding a halogen only, and this halogen that I'm adding is going to be Br2. Okay, so remember, bromine doesn't go alone. Why? It has 7 electrons around. It has 7 valence electrons. Okay, so if you just have bromine by itself, it'll have that one space. Remember, we have to fulfill the octet rule. So it either will have a hydrogen bonded to it so that it fulfills the octet rule, or it has another bromine atom attached to it. Okay, so it comes in pairs, or it comes with a hydrogen, because we want to fulfill the octet rule. So in this case, because my final product has 2 bromine atoms, I need to add bromine coming in pairs. So then, what do I have as my final product? Well, I have 3 carbon atoms, okay, and this double bond that I have there, well, assuming this is 1, and that's 2, and that's 3, remember I had a double bond, but I'm gonna now have a bromine on the first one, a bromine on the second one, and then I have hydrogen atoms surrounding it. Okay, I know sometimes my H's look like N's, but you are not at that level where you're dealing with nitrogen in these organic compounds. Okay, so this is our final product. which would be 1,2 dibromopropane. Okay, so we're done. We have our first reaction, or step 1, step 2, step 3. We know what it is. So now let us answer the questions. Okay, I'm gonna put all of this in a bubble, and then you can then answer the questions, and then we'll be done with question 4. All right, so using condensed structural formulae, write down a balanced equation for step 1. Indicate the reaction conditions on the arrow. I forgot about the reaction conditions. Okay, let's see how far we get. Okay, so now condensed structural formulae. I've drawn out structural formulas. Yeah, structural formulas without the hydrogens for saving time. Okay, so step 1, condensed structural formula, balanced equation. So basically we have but2ene. Okay, I'm just gonna take it down a bit so that you can see. So for 4.2.1, I had CH3. Okay, condensed at CH3, then I have CH, then I have CH, and then I have CH3. Well, I have space, and then I'm adding hydrogen to it, and then we are getting butane. So that will be CH3, CH2, CH2, CH3. Guys, sorry. Yeah, I'm running out of space here. Let me just rather go down instead of trying to put everything together. We'll keep going up and down, it's fine. Okay, so let's just put it out nicely. So we have 4.2.1, we had but2ene, so it is CH3, CH, CH, and CH3. And then this is hydrogenation, the addition reaction. And then what did it give us? It gave us butane. So CH3, CH2, CH2, and CH3. Now with an addition reaction, such as hydrogen, what are the reaction conditions? Okay, I forgot. I'm gonna be honest. I forgot. Yeah, and I have this table. I don't even have my phone with me, but I have this table showing me all the reactions. I really forgot. So let me pause and look for them. But I'll actually write down the reaction conditions at the end. Let's just move on. But yeah, so, and then write down a balanced equation. So how many carbons do we have? We have 4 carbons. How many hydrogen atoms do we have? We have 3, 6, 8, 10. 3, 6, 8, 10. Okay, cool. I'll come back to the reaction conditions, guys. Bear with me. Okay, write down the type of reaction in step 2. So we said step 2, that would be cracking. I don't know if you remember, but yeah, it's basically cracking. And then 4.2.3, write down the IUPAC name for compound B. Well, compound B. So reaction 1, we had butane and then crack. So we had methane and propene. Okay, I don't know if they want us to actually talk about methane, but it's basically propene. I think that's the one that they're interested in. Propene. Yeah, that is the IUPAC name. You don't even have to say 1 propene. It's just going to be this propene. Okay, and maybe if you want, you can put in brackets that we actually had methane as well due to cracking. Okay, but that's not required. I think propene is the one that they want. And then 4.2.4, using condensed structural formulae, write down a balanced equation for step 3. Okay, so for step 3, you had propene, right? So propene, because it looks like this, like I said, it doesn't matter which side you put it. So you have that, and that. So the condensed structural formula, it would be CH2, CH, CH3. Or it would be CH3, CH, CH2. Okay. So write down a balanced equation for step 3. So we have that propene and we are adding bromine, and then we are getting CH2 Br, and then we have CH Br, and then we have CH3, and they said it has to be balanced, right? So we have 2 bromines here, we have 2 bromines, we have 3 carbons on the left, we have 3 carbons on the right, and then the amount of hydrogens, well, we have 2, 3, 6, 2, 3, 6. Yeah, that is a balanced one. Now, coming back to the reaction conditions, I think with cracking, guys, no, these are the reaction conditions here. If you're going to add hydrogen, which I believe will come as a gas, I think you would have to have heat. Let me just check in my textbook, but I don't like this one that I have with me. It's not the one that I like. I normally use Mind the Gap. Mind the Gap has nice tables where it actually shows you the reaction conditions. But what did we do there? We hydrogenated it. So the reaction conditions, the catalyst there could be platinum. Okay, I think I've seen them use a lot of, in many examples they would put there platinum. I thought maybe they would have heat, but it is just platinum for hydrogenation. So that is a catalyst. You can either have platinum or nickel or palladium. Okay, so you can have nickel or palladium, but I like platinum. I've seen platinum a lot, so that is the reaction condition, guys. I got it. In an exam, I would have probably guessed something, but I totally forgot about platinum. I would have probably said heat, but it doesn't make sense. Heat, you normally use it to break apart, like for cracking. But yes, guys, so that is it for question 4. Thank you for tuning in. Please share this information with someone who would really, would appreciate it. Like grade 11s going to matric next year in 2022, as well as those who are upgrading. Okay, thank you guys. Bye.
Well, welcome to MV Tutors. My name is Figa, and I'm going to be your tutor today. So we are doing the 2021 November Physical Science Paper 2. We are now on question number 5, and as you can see on my side here, that's what we're going to be doing. So if this is what you're looking for, then you came to the right place. Let's get right into it. Okay, so it says the reaction of 15 grams of impure sample of calcium carbonate, there we go, with excess hydrochloric acid, there we go, of concentration that is used to investigate the rate of reaction. The balanced equation for the reaction is that, as shown, okay. The volume of carbon dioxide, CO2, produced is measured at regular intervals. A sketch graph representing total volume of carbon dioxide gas produced as a function of time is shown below. Okay, so we got volume on the y, time on the x. Cool. Define the term reaction rate. So basically, as you know already, reaction rate is just the rate of the reaction. Also, you could also say that it's just basically the change in concentration per unit time, or the change in reactants, or the change in products per unit time. Okay, and then 5.2, give a reason why the gradient of the graph decreases between T2 and T3. So if we look here between T2 and T3, okay, there's a decrease there. It means it just simply means that the what are these, the reactants are being used up. Basically, I can say that. Let me write it down for you. So that is 5.2. The reactants are being used up. It's as simple as that. Okay, the reactants are being used up. Okay, and then the changes in the graph between T1 and T2 are due. Okay, let me just zoom out so I read the whole thing. Changes in the graph between T1 and T2, okay, are due to temperature changes within the reaction mixture. Is the reaction endothermic or exothermic? Okay, so there's something that you need to know here. 5.3.1, you know, increasing, this is just theory work. Increasing temperature favors the endothermic. So all we have to do here is to see which one was favored, and that one will be endothermic. So let's see. An increase in temperature, the volume, increase the volume of CO2. Is CO2 a reactant or a product? So CO2 is a product. So an increase in products, that means that the reaction is therefore endothermic, because the products increased, they were favored, the products were favored, so the reaction is endothermic. Okay, and then it says explain the answer by referring to the graph. I just said it. Okay, so this will then be increasing the temperature favors the endothermic. So then 5.3.1 will be endothermic, and then 5.3.2 will be increasing temperature favors the endothermic. Therefore, since there was an increase in products, thus it rendered it endothermic. Okay, and then it says the percentage purity of the sample is 82.5%. Okay, remember they did say it's impure. This 15 gram is impure, meaning it's not just calcium carbonate, there's something else. But now they are saying 82.5% is actually the pure part, is the calcium carbonate. Then they say calculate the value of X on the graph. Where's X? Okay, there. So that's the volume they want. On the graph, assuming that the gas is collected at 25 degrees Celsius, take the molar gas volume at 25 degrees Celsius as 24,000 centimeters cubed. Okay, cool. Let's go. So this will now be 5.4. So I like to work backwards. So what do we have, and what are we asked to solve? We are asked to solve the value of X, and the value of X is a volume, and we are given a molar gas volume. So physics is most of the time is just making sure you choose, when it comes to the calculations, you choose the right formula first, and then you work from there. So the formula that involves a volume and molar volume is number of moles is equals to volume over the molar volume. Okay, so if we look at this thing carefully now, if we look at it carefully, what we have is that we don't know what the number of moles is. Volume is what we'll be looking for, but the VM, the molar volume, we have it as 24,000. Okay, and it's in centimeter cube, so let's just take note of that. Now we need to solve the number of moles, right, so that we get the right answer. So we'll come on the side, this side, to solve that. Now let's use what we have actually been given. So first of all, they say 82% is pure calcium. Okay, there we go. We have been given that. And then what other information do we have? Okay, let's go back to the question. It said 15 grams. Okay, so number of moles, we know number of moles is mass over molar mass, right? And then we've been told that actually to solve the number of moles we need the mass, and the mass we've been told that is actually 15 grams. But this 15 grams is in pure. Now we need it to be pure, right? So then we'll multiply. We want 82.5% of it. 82.5 is like 82.5 divide by 100. Okay, that's just the mass. And then the molar mass, it's the molar mass of calcium carbonate. And if you go to your periodic table, you add them up, add up these masses, you'll find that it comes up to 100. We've done a lot of them, that molar mass of, we've done it a lot. Molar mass of calcium carbonate, it always adds up to 100. So okay, that's that. Now let's put this in a calculator. We'll solve the number of moles. This is of calcium carbonate, right? Calcium carbonate, just so we're clear. Okay, and then we'll say 15 times 82.5 divide by 100, because that's what percent means. And then under here we'll just say 100, and then we get, that's gonna be equals to 0.12375. This is the number of moles of calcium carbonate. Now what we need to do next then is go take a look, what is the ratio, because here, what were we talking about? We want the percentage of X, and X there is carbon dioxide. So we need the ratio between carbon dioxide and calcium carbonate. Okay, so if we look here at this formula, balanced equation rather, we can see that it's 1:1. 1:1. So that means if the number of moles of calcium carbonate is okay, that's X, is actually 0.12375, that also means, you know, the number of moles of calcium of carbon dioxide is the same. Okay, so we can come by this side and say 0.12375. Now there's something else about this. Okay, this is in centimeter cube, right? And x is also given, they wanted us to give it in centimeter cube, so we'll keep it like this. So to solve for v, then the volume of carbon dioxide is just equals to that times that. So I'll put that, I'll just say times 24,000, and then I get 2,970 centimeter cubes. That's our final answer. Okay, well, I hope you followed over there. Let's go to the next question. Then it says, how will the reaction rate change if 15 grams of pure sample of calcium carbonate reacts with the same hydrochloric acid? So what is essentially happening here now is that we are actually increasing, this is 5.5, we are increasing the concentration of carbon of calcium carbonate rather, and it's a reactant. So if we increase the reactant, there's more of the products being produced. So it says here, how will the reaction rate, okay, react with the same, okay, so the reaction rate will increase. Okay, and then 5.6, it says use the collision theory to explain your answer. So there's an increase in concentration, okay, number one. That means there is also an increase in collisions. It's actually leads to an increase in effective collisions. Okay, and an increase in effective collisions means there is an increase then in rate of reaction. That's it. Okay, I hope you understood everything that we did, but in the event that you didn't, please do contact me. I would love to be your tutor. Just contact me via my email, which is www.mvtutors.co.za, or you can WhatsApp me on 076-312-1107. Now, before you do contact me, please make sure you speak to your parent or your guardian, because remember, at the end of the day, they are the ones who will be paying for my tutoring services. Okay, so thank you so much, and I appreciate you. Well, welcome to MV Tutors. My name is Figa, and we are doing the 2021 November Physical Science Paper 2, and we are now on question number 6. Well, if this is what you are looking for and you want to know how to do it, then stick around. At the end of this, hopefully you would have understood everything. Well, let's get right into it. Question 6.1 says, define the term chemical equilibrium. I don't know, they love this question. They ask it every time. But basically, as you know already, it's when the forward reaction is equals to the reverse reaction. But before that, it says consider the balanced equation below for a hypothetical reaction that takes place in a sealed 2 decimeter cubed container. All right, so we've got P Q, and then PQ. Then it says the amount of each substance present in the equilibrium mixture at 300 K is shown in the table below. Okay, so those are the number of moles of each. Then it says the temperature of the container is now increased. Okay, so increasing temperature now. When a new equilibrium is established, it is found that 1.2 mole of P is a reactant, okay, is present in the container. Is the heat of reaction positive or negative? Okay, so now what happened? Let's just talk about this. An increase in temperature favors the endothermic, okay, and the enthalpy of the endothermic is actually positive, and the enthalpy of enthalpy is this change in H of the exothermic is negative. Now, remember I said an increase in temperature favors the endothermic according to Le Chatelier's principle. So that means since P is a reactant, the reverse reaction is favored. So if that means that the reverse reaction is endothermic. Now, if the reverse reaction is endothermic, the opposite is true for the forward reaction. So that means the forward reaction is exothermic. Okay, and an exothermic, let me just say that at 6.2.1 is the heat. An exothermic reaction has an enthalpy or a heat that is actually negative. So we'll go with negative. And then 6.2.2, use Le Chatelier's principle to explain the answer. Well, I've just explained it, but basically an increase in temperature favors the endothermic reaction. Okay, and the reverse is endothermic here. The reverse reaction, let me put that word. The reverse reaction is favored because P increased from 0.8 to 1.2 as we've been told here. Therefore, the forward reaction, okay, so if the reverse is forward, that means it's endothermic, right? Endothermic. Therefore, the forward reaction is exothermic. And the exothermic has a negative. Thus, a negative. Well, I want to say enthalpy, but I'll use the words they used here. So negative heat. Okay, that's it. And then 6.2.3, calculate the equilibrium constant at 350. Okay, so there we go. Let's do just that. So we are now at 6.2.3. all right, so I'm going to use the rice method, right? So basically we'll have R, which stands for ratio in mole, and then I, which stands for initial in mole, and then we'll have rice E, we'll have the change in mole, and then we'll have the equilibrium in mole, and then rice E, it's still the equilibrium, but now I want it in mole divided by the volume per decimeter cubed. Cool. And then the reactants that we have, I have P, okay, a line, and then the other reactant is Q2, and then a line. And then to separate my reactants from the product, I put a double line, okay, and then I put PQ, that's the products, just to distinguish between the two. Okay, and then also what I want to do on the change right now, I know that when it comes to reactants, I always subtract the change. So I'll put a subtraction and I always add the change. Okay, there we go. Now I can just, you know what, I should have used a different color for my table. But anyway, I'm gonna do this. Change. You know, I could do it in a more tidy way, where you know I draw with my ruler, because I have a ruler here, but it'll take time. So I'm just gonna leave it like this, untidy. I'm sorry. But anyway, let's start with the ratio. Let's fill in what we have been given. So the ratio, I have 2 for P. Okay, let me use a different color. Let's go 2 for P, and then 1 for Q, and then 2 for PQ. Those are the ratios. And then these now become equilibrium, because remember these values are at 300K. So these are my initial. So I'm starting with P is 0.8, Q2 is 0.8, PQ is 3.2. And then I've been told that the new equilibrium established is found at 1.2 mole of P. So P has an equilibrium of 1.2. Okay. Now, that's all we've been given. The rest we have to solve it for ourselves. Okay. So that's what we've been given. Okay, let's see. Now, to move from 0.8 to 1.2, okay, I actually need to add, right? Because 1.2 is more than that, and I know that reactants, you always subtract them. So let me get a calculator first and say, okay, 1.2 minus 0.8. That gives, I need to add 0.4, but I already have a minus here. So what I need to do is put minus 0.4 here in brackets, so that I'll have a minus and a minus, and then it will give me a positive. It will give me a positive. Remember, a minus and a minus gives you a positive. Okay, so now there's a relationship between the ratio and the change. That's where the relationship is. So 2 is to 1. Okay, so 2 is to 1. That means for every 2 moles of 0.4, there's 1 mole of that. So to get 1, I'm going to just divide it by 2. It's basically I need to add 0.2. So then I'll put minus 0.2 in brackets, so that I have 0.8 plus, so let me just say plus 0.8, then I get 1. Okay, also here there's a relationship between P and PQ. The ratio is 2 is to 2. So if this was a minus 0.4, then also here in brackets, remember the relationship is 1 is to 1 because it's 2 is to 2. So I'll put minus 0.4. Okay, and then 3.2 minus 0.4, and I get 2.8. And the reason we did that is because remember we have a plus here, so it's plus minus. Okay, plus minus. Now I just need to divide these numbers by the volume. And remember the volume, they told us it's 2 decimeter cubed in the question, right over there. So all we have to do then is to say 1.2 divided by 2, and we get 0.6, and then 1 divided by 2 is 0.5, and then we have to say 2.8 divided by 2, and then we get 1.4. Okay, cool. Now we have all the values that we need, okay, to complete this calculation. These are just the values that we need, the equilibrium one, because now remember they said calculate the equilibrium constant. We know that the equilibrium constant is the products, and the product is PQ, and the number of mole is squared, so it is 2, so that 2 becomes an exponent, and then divided by the reaction. So a reaction of P has to be squared, and then the concentration of as well Q, so it's Q to the power 1. Now PQ is 1.4, so about that, 1.4, and it should be squared, divided by P, which is 0.6, should be squared, times Q, which is just 0.5. Right, let's put this in a calculator. So open our fraction, put 1.4 there, and it's squared. Come downstairs, 0.6 squared times 0.5, just like that. And then our final answer, our Kc value then is 10.89. So that's our Kc. And we are done with this question. I hope you followed. Okay, now let's see the next question. It says, how will the equilibrium constant calculated in 6.2.3 be affected when the volume of the container is decreased at constant temperature? Choose from increase, decrease, or remain the same. Okay, so how will the equilibrium constant, so we are talking about the equilibrium constant here specifically. Okay, 6.2.4, and we know the only thing that changes the equilibrium constant is temperature by theory. Okay, so here we are changing the concentration. Okay, how will the equilibrium constant be affected if we decrease when the volume of the container is decreased at constant temperature? So the fact that temperature is remaining the same, it means that also the equilibrium constant will remain the same. And they say give a reason. The reason is because only temperature change changes the equilibrium constant. Equilibrium constant. That's it. Okay, and the next question says more Q2 is now added. So Q2, what's Q2? It's a reactant, is added to the reaction mixture at constant temperature. How will each of the following be affected? Choose from increase, decrease, or remain the same. Okay, let's look at this. Now, the first one is the yield of PQ. Or what happens to PQ if you are adding more Q2? PQ is a product. If you add more Q2, then PQ will definitely increase. Okay, so now this is 6. I'll change my pen. Let's go for red. 6.3.1. The yield of PQ, it will increase. Okay, it increases because we increased Q. 6.3.2, the number of moles of P. Now what is P? P is a reactant. So if I'm increasing Q2, that means P is being used up. Therefore, it must be decreasing. So P will decrease because we are increasing Q2. All right, that's it. Now I hope you understood everything that we just did, but in the event that you didn't, please, I would love to be your tutor. All you have to do is contact me via my email, which is www.mvtutors.co.za, or you can WhatsApp me on 076 312 1107. Now, before you do contact me, please make sure you speak to your parent or your guardian, because remember, at the end of the day, they are the ones who will be paying for my tutoring services. Okay, other than that, I do hope you understood, and all the best. I appreciate you. Well, good day to you. Welcome to MV Tutors. My name is Figa and I'll be your tutor today. We are doing the 2021 November. This is your final exam of the physical science paper 2 now. Okay, so if this is what you're looking for and you want answers to these questions, then you came to the right place. Stick around here and I hope at the end you will understand. Well, let's get right into it. It says sulfuric acid, okay, which is one of the strongest acids, ionizes into 2 steps as follows. Okay, define, and the first question, define an acid in terms of the Lowry-Bronsted theory. Well, according to this theory, acid is a proton donor. Okay, it donates a proton. Now it says the next question, 7.1.2, write down the name or formula of the substance that acts as an ampholyte in the above equations. Well, first of all, you have to understand what an ampholyte is. And an ampholyte is a substance that actually acts as both an acid and a base. Usually it's things like water, but we have to do the investigation We can't just assume it's always water. Okay, so let's see. The first equation we have is H2SO4, okay, plus water, which is H2O, and it gives you HSO4 plus H3O. So let's investigate this. Which one is, okay, we know this is an acid already, they've told us. It's been given, so then this becomes the base automatically because that's an acid. That means, so this donated, that means this is now the conjugate base, okay, for this acid, and then this one is now the conjugate acid. Okay, so in this step water was a base. Let's check the next step. Then we have my bad, is HSO4 plus water again, and it gives us SO4 plus H3O. Okay, we know through theory as well that this is still an acid, HSO4. It's a weaker one, but an acid nonetheless, which means this is a base. Now SO4 here is now a conjugate base because it has to do with this acid, and then this base, that means this is a conjugate acid. Okay, so let's check this out. H2SO4 is an acid here on the first one. It's not on the second one, so it doesn't count. Let's look at water. It's a base on the first equation, and it's a base again on the second equation, so it is not an ampholyte in this case. Now let's look at HSO4. It's a base on the first equation, and on the second equation it's there, and it's an acid, so it's a base and an acid. Therefore we can conclude then that therefore HSO4 is the ampholyte. What is the spelling of ampholyte? Ampholyte. And they say give a reason for the answer. Well, it's because it acts as both an acid and a base. Cool. All right, let's read the next question. 7.1.3, the conductivity of the solution of HSO4 and the sulfuric acid are compared. Which solution will have a lower conductivity? Explain your answer. Okay, so for that we need to know their individual constants. So that's the Ka values. So now we're looking at question 7.1.3. Okay, so it said compare which one has lower conductivity and explain your answer. So the one with the lower Ka value is the one that has a lower conductivity. So the Ka value, the A stands for acid. So the acid in the first equation was sulfuric acid, and it is 1 times 10 to the power 3. And then the acid on the next equation is the HSO4, which is 1 times 10 to the power minus 2. So then our answer then is that the one with the lower conductivity is H2. Why? I said give a reason for your answer. Because it has a lower Ka value. Okay, that's it. That's it. That's all we're gonna say there. Let's move on. And then 7.2 now. The pH of a hydrochloric acid solution is 1.02 at 25 degrees Celsius. Calculate the concentration of HCl. So they gave us the pH. Okay, so we can calculate concentration based on the pH. So now we're on 7.2.1. We know that the pH formula is equals to minus log of H3O. Okay, and also we know by definition that the concentration of HCl, okay, of HCl is equals to the concentration of H3O. Okay, that's just theory because this is a strong acid, so it ionizes completely. So then that it's equals to the concentration of your H3O by theory. Okay, so we've been given the pH. Let's just solve. So if we solve the concentration of H3O, then we basically solve the concentration of HCl, hydrochloric acid. So pH is 1.02 is equals to the minus log of that concentration we're looking for. And if we make that the subject of the formula, it's gonna be equals to 10 times to the minus the pH, which is 1.02. Now these are your rules. These are mathematical gymnastics. These are the rules of mathematics of how to solve exponents using logs and vice versa. So here we have 10 to the power negative 1.02, and our answer is 0.095. Okay, remember this is the concentration of H3O, and so we can conclude and say therefore the concentration of HCl is equals to also 0.095. Now what are the units of concentration? Well, it's mole per dm cubed. Cool. All right, let's go see what the next question is. It says now this HCl solution reacts with sodium carbonate there according to the following balanced equation. Cool. Now 50 centimeter cubed of hydrochloric acid solution is added to 25 centimeter cube. So you're taking 50 and you're adding 25 as well. So that makes a total volume of 75. Okay, but the 25 is of 0.075 moles of that. Okay, solution. Now 7.2.2 says calculate the concentration of excess HCl in the new solution. Okay, so you know I like to work backwards with these types of questions. Well, with every type of questions really. So by backwards I mean let's start at the end and work our way. So calculate concentration. So what is the formula? The concentration that we need to calculate is the concentration is equals to number of moles divided by volume, right? So let's check this. Do we have the volume? Yes, we definitely have the volume. It's 25 plus 50, which is 75. But to convert it to decimeter cubed, we divide by 1000. Okay, so now we just need to solve the number of moles so that we will be able to put this to solve the final concentration. Okay, we'll do that on the side. We'll use the information that we've been given. So we know that we have been given here concentration of that and also its volume, so we can solve number of moles. So let's say number of moles of Na2CO3 is equals to concentration times volume, right? So that means concentration is 0.075 times the volume is 25 centimeter cubed, but to convert it to decimeter cubed, we divide by 1000. Okay, let's put this in a calculator. So we have 0.075 times 25 divided by 1000, and that's equals to 1.875 times 10 to the power minus 3. Okay, now we need to go check what is the ratio between Na2CO3 and, remember, we want H, we're looking for HCl, and the ratio is such that HCl we have 2, and that one is also here, and it's 1 mole. See, sodium carbonate, it's 1 mole, so it's 1:2. So I want to solve for X, and I know that this one is 1.875 times 10 to the power minus 3. So to solve for X, really what I have to do is just multiply by 2, because 1:2. So then I have to just say 2 times 1.875 times 10 to the power minus 3 will give me the number of moles of HCl. Okay, let's put this in a calculator. I'm just gonna say times 2, and then I get 3.75 times 10 to the power minus 3. Now check this out, it gets tricky over here. This is the number of moles that are actually used. Okay, they want the excess number of moles, and remember, excess means you take the initial and then you subtract the used to get the excess. So this one was used, these are the number of moles used, so we need to calculate now the number of moles that are initially given. And remember, number of moles is given by concentration times the volume. Now this is the number of moles of HCl, the initial one. Initially, if we look here, the concentration of the initial number of moles are the ones we solved previously, which is 0.095. So that's the one we'll put over here, 0.95 times the volume. The initial volume is 50 centimeter cubed, because they say 50 centimeter cubed of HCl solution is added. So initially we have 50 because that's the one that was added. And to convert it, we divide by 1,000. Okay, so let's put this in a calculator. We have 0.095 times 50 divided by 1,000, and then we get 4.75 times 10 to the power minus 3. Now these are the initial number of mole. Remember, here we are talking about the number of moles that are in excess. Okay, excess. So we have to solve the number of moles that are in excess, and that's what we're trying to do over here. Now, to get the excess number of moles, it's still HCl, but we have to say the number of moles of HCl that are initial minus the ones that are used up. So the initial ones is 4.75 times 10 to the power minus 3, minus the used ones are 3.75 times 10 to the power minus 3. Let's put that in a calculator. I'll just say minus here. 3.75 times 10 to the power negative 3. Oh, okay. Yeah, that's fine. We get 1 times 10 to the power minus 3. So these ones are now the one that is in excess. So when we come back up here, the number of moles that we put here, we put the ones in excess, which is the 1 times 10 to the power minus 3. Okay, so that's what we put in the calculator. So we'll say 1 times 10 to the power negative 3, and then we need to go downstairs and say 75 divided by 1,000. Okay, and then our final answer is 0.013 mole per decimeter minus 3. That is now the concentration that is in excess of HCl in excess. Wow, this was a very long question. As you can see, I think it was worth 8 marks. But 8 marks. I hope you understood everything that I did. You can always just rewind and rewatch if you didn't. But in the event as well that you didn't, I would love to be your tutor. Just contact me via my email, which is www.mvtutors.co.za, or you can WhatsApp me on 076-312-1107. Now, before you do contact me, please make sure that you speak to your parent or your guardian, because remember, at the end of the day, they are the ones that are going to be paying for my tutoring services. Other than that, well, that's it from me. Enjoy the rest of your day, and I appreciate you.
Hello everyone and welcome to NV Tutors. I'm Solo and I'll be looking at question 8 with you guys. This is the second last question. I was actually shocked that it ends at question 9, this paper. We don't have question 10. But it's all good. They distributed the marks accordingly so that you still are, headed towards 150 marks. So yeah, please do not forget to like our channel and also subscribe. No, like our videos and then subscribe to our channel. Yes, that's the flow. And yeah, so I'll be doing question 8 with you guys. I don't even have my hat on. It's so hot. But yeah, let's just do it. The table below shows two half cells, A and B. Okay, so as soon as you hear the word or see the word half cells, you must know this type of electrochemical cell must be a galvanic or voltaic cell. Okay, it's not going to be an electrolytic cell. Okay, and then what else do we have? It is used to assemble an electrochemical cell under standard conditions. Guys, the moment you hear standard conditions, you must tell yourself, or you must remember that the pressure that you have, if you will be dealing with pressure, it'll be 1 atmosphere. The concentration that you have will be 1 mole per cubic decimeter, and the temperature that you'll be dealing with is 25 degrees Celsius. Okay, yeah. So we have half cell A, where we have copper 2 plus ions, and then we have that stroke over there, which is indicative of what is it, your electrode. Okay, so your electrode in this case would be the copper, the solid, and then half cell B, you have silver there. Okay, yes, in aqueous solution, and then you have that solid over there. If you had a double stroke, that would indicate the salt bridge. Okay, so now 8.1. So basically, if I were to draw this, yeah, this is what I'm actually coming to. Okay, then you have your salt bridge here. Okay, and then you have your cotton wool plug somewhere there. Then you have your salt that's in that salt bridge. Okay, then you have your electrode and your electrode as well. Okay, and then you have your electrolyte over there. Okay, and then you have your connecting wire with your voltmeter reading, voltaic cell. Okay, and then at one point you're gonna have your cathode and then your anode. I like putting the anode this side, but we haven't yet established where the anode is. I mean, what is actually the anode? And then you have your cathode. Remember, cathode, that is where reduction occurs, and your anode, that is where oxidation occurs. Okay, oxidation, and your anode would be negative. Ne? The electrons will be flowing all the way to your cathode. Okay, and your cathode will be positive. And you're like, what? It's getting electrons, why is it positive? Well, yeah, story for another day. Lessons will be loading soon, so you'll have your answer there. All right, so now you'll see, yeah, that's pretty much what's happening. We will then see where is the copper, what's happening with the copper, what's happening with silver. Okay, so state the energy conversion that takes place in this cell. 8.1. Well, with a galvanic cell, it goes from chemical energy all the way to electrical energy. Okay, that is the conversion. This is like, it happens spontaneously as well. Whereas with your electrolytic cell, it goes from electrical energy to chemical energy. So you need electricity for this thing to start happening, okay? And then 8.2, let's just take this paper up. Calculate the mass of silver nitrate, okay? used to prepare 150 cubic centimeters of the electrolyte solution in half cell B. Okay, so we're sort of like getting more information. So if you want to calculate the mass of silver nitrate, okay, what do you need? They've given us a volume here. All right, so we know our volume is 150 cubic centimeters. We want to convert that to cubic decimeters. So what you're going to do, you're going to divide by 1,000, and then you're going to have 0.15 cubic decimeters. Okay, and then you have your concentration. Your concentration is 1 mole. Remember standard conditions? So now, if you want to determine the number of moles there, so this is where I'm going. Want to get number of moles, and then you can get our molar mass, and then you can get our mass. Okay, so the number of moles would be the concentration times the volume. So it'll be 1 times 0.15, and that's pretty much going to be 0.15 mole. Okay, now once you have that, you need to go and determine the molar mass for silver nitrate. Okay, so we have silver, you have nitrogen, and you have 3 times oxygen. So your silver, if you look at the periodic table, I just have the values with me at the moment. I need to just load the periodic table, but it's fine. Nitrogen should be 14, yeah? And then oxygen should be 16. So 3 times 16. So if we calculate all of that and get the sum of it, so it'll be 108 plus 14 plus 3 times 16, and that is 170 grams per mole. Okay, so now we have the molar mass, we have N, and now we're looking for the mass. Okay, so therefore the N is M over M. So if you want the mass, you're going to have the number of moles multiplied by the molar mass. Number of moles is 0.15. The molar mass is 170 grams per mole. So if we were to multiply this by 0.15, we get the mass of silver nitrate to be 25.5 grams. Okay, so that is that. And then 8.3. Define the term reducing agent. Okay, so agents actually like do the opposite. If you know that oxidation is when you are losing electrons. Okay, so you're losing electrons. So what helps you to lose those electrons, what helps your element to be oxidized is the reducing agent. Okay, not the oxidizing agent. So basically the reducing agent okay, that's where oxidation occurs. Therefore, that would be the loss of electrons. Okay, and then 8.4.1. Name or formula of the reducing agent. So if you have your reducing agent, that's basically where oxidation occurs. And if that's where oxidation occurs, that's basically your anode. Okay, remember our galvanic cell here is incomplete. We need to complete it just so that we see what is happening. And for you to see which one is the reducing agent, you're going to have to consult your table of standard reduction potentials. Whether you use table 4.4a or 4b, for me doesn't matter. It will give you the same answer. Okay, so the same with 8.4.2. When they want the balanced equation for the reaction that takes place, you will be assisted when you use that table. So I do not have the table with me at the moment, so I'm going to get it and then we're going to continue. Okay, so I got the table of standard reductions. Okay, I'm gonna probably use 4a because it's first in line. Okay, so let's just recap. Write down the name or formula of the reducing agent. So what I'm gonna do, I'm gonna look at the copper. Okay, and I'm going to compare it with silver. And the one that has the highest reducing ability, that is the one that is the reducing agent. Okay, so let's just have a look. So if you can see copper, yeah, there are different coppers here available. So the first one you can see here, but it just has one positive ion. That's not the one that we're looking for, right? Then we get here and you can see that this is the copper that we're looking for. Okay, but the arrows on the side, we're gonna have to look at the arrows on the side. So here it says increasing oxidizing ability. Okay, so it means that when you go up the table, that's where you have oxidation, or rather oxidizing agents, okay, increasing, like the ability to for it, or rather, yes, let me just stick to oxidizing agents. So if you look at oxidizing ability, it's similar to saying oxidizing agents. So the powerful oxidizing agents will be the ones where, as the table goes up, okay, it strengthens in that regard. Okay, and then on the right hand side you have increasing reducing ability. Okay, so here that is like saying reducing agent. So as you go down, you get those that the reducing agents are pretty much strong going down. Okay, so we're gonna have a look to see which one is actually the reducing agent. So we know what copper is. Copper 2 plus is here, plus 0.34, and now we need to look for silver. Okay, so is silver down there or is it up there? I'm just gonna start looking from the top. So we have fluorine, cobalt, and oh, here is silver. So silver is actually on top, right? So silver oxidizes better, and no, cancel that, because going down, reducing ability, reducing agent. So silver, yeah, it's on top, but copper 2, now I've lost it, there it is. So copper 2 has a better, better reducing agent, if I could say. So if we get back to here where it says name or formula of the reducing agent, because copper is stronger going down, we're going to go with copper. Okay, so I'm just going to write that down. I hope I didn't confuse you with that explanation, but that's how you basically gauge it. Okay, so it'll be copper. Okay, and then so we're going to have to write a balanced equation for the reaction that takes place. So what actually happens? Okay, so if it's a reducing agent, it means that it is oxidized, right? And if it is a oxidizing agent, it means it has been reduced. So looking at our, now I've gotten rid of my thing. So silver, it is up here, ne? It has a higher oxidizing ability. Okay, so if we look at silver, oxidizing ability, okay, meaning that it is reduced. So silver is the one that is reduced. And then copper, which is here, it has a higher reducing ability. This is reduced, therefore copper is oxidized. Okay, if you want to make sure that you are good with that explanation and you're actually on the right track, normally in your galvanic cell you would have copper on your cathode and zinc on your anode. Okay, so zinc should have a better reducing ability. Okay, so if we were to look, zinc should be lower than copper. That's what I'm getting to. So copper 2 plus is up here, zinc should be lower than it. If zinc is not low, yeah, so there is zinc. Definitely zinc is a good reducing agent, much better than copper, meaning that zinc oxidizes if you're comparing zinc with copper, and copper is the one that reduces. But in this case, silver is the one that is reduced and copper is the one that is oxidized. So if we go back to our sketch to fill in which one is reduced and which one is oxidized, we have determined that Copper is the one that is oxidized in this case. I know we're not used to that. We're used to copper being the one being reduced. And then the one that is being reduced in this case is silver. Okay, so yeah. So yes, now that we know that, we can write down our balanced equation. Okay, so we're going to talk about which one is reduced, which one is oxidized. So we're going to go back to our table over there. And let's go back to silver. So silver is here. Okay, so we said silver is reduced. And remember, when it comes to the one that is reduced, remember if it's reduced, it means that it is on the, what did I do now? If it is reduced, it means that it is the one on the cathode. And if it's oxidized, it's on the anode. Okay, so at the cathode, whatever is written, like the way it's written on the table, you take it as is. Okay, you don't swap anything around. So we have silver, which is an aqueous solution. That's silver, the ion, and then we have an electron. And then please guys, do not use double arrows. Okay, in this case you don't have reverse reaction. It's not a closed system. Okay, and then we have the solid there. All right, so that is what happens at the cathode. Now what happens at the anode, you are going to have to swap it around. What do I mean? So there's our copper. Okay, no, that's not the one. We need copper 2+. Okay, so at the anode, you're going to have to swap it around. So you have the solid, all right, and then it becomes ions. Copper 2+ plus 2 electrons. Okay, so now we need to balance the equation. Okay, what was the question? Balanced equation. Yes, so we need to balance here. I'm going to use green. So we see here we have 2 electrons. And here we have 1 electron. So what are we going to have to do? We're going to have to multiply this whole thing by 2. And you have to multiply this by 1. Okay. So when we finally write down our answer, okay, we're going to have silver multiplied by 2. Okay. And we're going to have copper there multiplied by 1, which just remains. And then on the other side of the arrow, you're going to have 2 again, silver, the solid, and then you're going to have copper 2+. Okay, so that is your balanced equation. Okay, so yes, we are getting further closer to the finale. Okay, so 8.5, calculate the initial EMF of the cell. So if you were to consult your formula sheet, okay, we would say that E cell is equal to reduction minus oxidation. I prefer using E cell. Okay, the fact that it has the 0 on top means that standard conditions apply. Okay, and those standard conditions, temperature is 25 degrees, concentration is 1 mole per cubic centimeter, and pressure is 1 atmosphere. So basically that's going to be the cathode minus the anode. Okay, the one thing that I really forgot to do was take down the values. Okay, at least we have highlighted it there. So for silver, we have the value of 0.8 volt. And then for copper, we have 0.34 volt. So for a galvanic cell, when you are calculating, the initial EMF, what am I doing now? You must make sure that at the end, your answer is positive. If you're getting a negative answer, guys, you did something wrong. Okay, please make sure. So at the cathode, we have our silver, and that voltage reading is 0.8. at the anode, we have copper, and that voltage reading is 0.34. So what is 0.8 minus 0.34? Well, that will be 0.36. I don't know. Let's check. Yeah. Well, like I like saying, you know what, in an exam situation, because you are high on nerves, just plug everything in the calculator. Even when it comes to 1 plus 1, put it in, because you might write wrong things. So yeah, 0.46. What did I say? Whatever I said was wrong. So 0.46 volts. Alrighty. And then 8.6. Okay, so 8.6, let me take it a little bit up. So 8.6 says, how will the EMF of the cell be affected if the concentration of the copper ions in half cell A increases? Ooh, I even forgot to say which one is A, which one is B. So, okay, but it doesn't matter. We know that half cell A, that's the copper. Okay, so that's fine. But now it says, how will the EMF of the cell be affected if the concentration of the copper ions increases? Remember, because of standard conditions, our initial concentration, it is 1 mole per cubic decimeters, right? So then it tells us that it increases. So the concentration goes from 1 mole to a higher value, okay? A value higher than 1 mole per cubic decimeter. Now it says, how will the EMF of that cell be affected? Will it increase, decrease, or remain the same? So to answer this, you're going to have to look at your balanced equation. And I've said this in preparation for actually not the preparation, but when we did the memo for the prelims, I actually said there's a rule of thumb. Okay, just really be aware of that. Okay, so rule of thumb. Okay, basically, if you find that applying Le Chatelier, you get something that is product favored, V, product favored, okay, then your voltage reading will increase, meaning that your EMF will also increase. If you get something that is reactant favored, okay, by reactant favored, I mean reverse reaction favored. By product favored, I mean forward. Okay, I think the camera is pointing the other way. But anyway, product favored, you're going to the right? So it's forward reaction favored. And then reactant favored, you're going to the left. So it is reverse reaction favored. That's what I mean. So if it's something that's reactant favored, then you know that your voltage will decrease. So ultimately, your EMF will decrease. Please, please, please remember this. So now let us see. According to our balanced equation, we are saying that for half cell A, the concentration is increased. So we are increasing the copper ion content. Okay, this is increasing. So what does Le Chatelier say? It says if you're going to increase anything on the product side, okay, think about a seesaw. So initially everything is balanced. You've reached chemical equilibrium. So that is our seesaw there. Okay, and you have your reactants that side, you have your products, everything is cool. But now the products become heavy because you've increased the concentration on the product side. Okay, so what happens if it becomes heavy? Now your products are there and your reactants are there. So what are you going to do to get a new balance, a new chemical equilibrium? Well, yep, that's what you're going to do. You're going to increase the reactants. Okay, so you're going to have to then increase the reactants, okay, such that the reactants also become heavy again, and then you've reached a new equilibrium. Okay, so that's how you can actually picture it. So we have increased the concentration of copper, right? So at that point, the products have increased. And then now to get a new equilibrium, you're going to have to increase the reactance. So your reaction will be reactant favored or reverse favored. Reverse reaction favored. Okay, so like we said, if it's a reverse reaction that's favored, then your voltage will decrease. So what are we going to say? Choose from increase, decrease, or remain the same. We're going to go with decrease. And on the note, ladies and gentlemen, we are done with question 8. I hope that it was good, that you found it not to be so very confusing, and I hope that I explained well. But yeah, thanks for tuning in, and see you again next time. Maybe this is the last time you'll see me since you're done with matric. So yeah, but don't forget to spread the word to the grade 11s that will be in matric next year, or for those who are upgrading. Okay, sharing is caring. Hi guys, and welcome to MV Tutors, and we are at the end. Question 9. Quite a short one. I'm glad, well, I'm sure you were glad when you got to this question. You're like, oh, it's gonna be short, we're almost there. So yeah, here we are, question 9. Another electrochemical cell. It looks like it's an electrolytic cell. So let us see. The diagram below shows a simplified electrolytic cell used to electroplate a ring. So with electrolytic cells, we know that we have electrical energy converting to chemical energy. So you need that electrical current. You need that electricity to be able for the reaction, the chemical reaction to occur. Okay, so here we have a ring. Okay, that needs to be electroplated. Okay, so you're gonna have your pure chromium metal, and this one, that's basically where oxidation occurs. So like we always say, it's gonna start losing some of its mass. It's gonna get almost at massless, but yes, the mass will become less. It will start losing some of its mass, whereas this ring here, we don't know what the original what it consists of originally. Is it just a cheap metal? Probably. So you're going to electroplate it with this chromium. Okay, so it's going to gain mass. All right, and yeah, here we have concentrated Cr3+, so chromium 3+. So 9.1 now says define the term electrolyte. Remember, you have your electrode, which is your pure chromium metal, okay, on the reduction, on the oxidation side. There on your anode, I wanted the term anode. So here at the anode, you have your electrode here, which is the pure chromium metal, and now here at the cathode, you have your ring. Okay, so now when it says electrolyte, it's talking about the solution. Okay, so what is an electrolyte? Basically, it is a solution consisting of ions. Okay, so the solution is not just plain water or anything. It's a solution consisting of ions. Okay, and those ions are capable of conducting electricity. Okay, and then 9.2, is the pure chromium metal the anode or the cathode? Not only way, but one of the ways you can see that this pure chromium metal is at the anode is, whatever is losing mass has to be at the anode, whatever it is gaining mass has to be at the cathode. Okay, so we're trying to get that pure chromium metal onto the ring. So the pure chromium metal is at the anode. At the anode, that is where you have the oxidation occurring. You're losing electrons. Okay, that's the reduction reducing agent. Okay, so it's at the anode. Give a reason for your answer. Okay, at the anode, because that is where oxidation occurs. occurs where you're losing electrons and the mass will reduce. Okay, so that's what I would say. And then it says, write down the half reaction that takes place at the ring. So here's what you have at the ring. First of all, you had ions, and those ions are going to then turn into chromium. I almost said copper. Turn into chromium, the solid. Okay, so we're going to have to, and remember at the cathode, however it is written on your table of standard reduction potentials, that's exactly how you write it for the cathode. So we're going to look for chromium 3 plus. And I have found it, I think. No, not yet. So I was looking here. That's not the one. We want the one that ends up being a solid. Now I see chromium 2. Oh, here it is. Chromium 3. Chromium 3 plus. You see it ends up being a solid. So we have chromium 3 plus, okay, in aqueous solution. And we have 3 electrons, okay, and then it turns into a solid. So that's what we're dealing with there. And that is the half reaction that takes place at the ring, okay, at the cathode. And then 9.4, calculate the total charge transferred when the mass of pure chromium changes by 2 grams. Guys, I have to admit, when I looked at this question before, I was like, huh? Because the equations that I know, remember current is equal to charge over time. And I was like, I don't have the current. I don't have the resistance or the voltage reading. I probably can get the voltage reading from the table of standard reductions, but I don't have the resistor. So how am I going to get I? Okay. So I had to consult. And upon consulting, I was reminded that it's not going to be, I'm not going to use this formula. Okay. It's going to be more than that. We're going to work here. But basically, the equation that you would use in this case, remember, if you're looking for the number of electrons, okay, it is equal to the charge, right, over the charge of an electron. Okay, so we know what the charge of an electron is. Now, can we get the number of electrons? If we can get the number of electrons, then we can calculate what the charge is. Okay, so basically, gonna go number of electrons multiplied by the charge of electrons. So let's see if we can get the number of electrons, because we already know that the charge is negative 1,6 times 10 to the power minus 19. So let's start with the information that we've been given. Okay, so we know that we have 2 grams of chromium. We have that C3 plus. Okay, so I'm gonna try to get the number of moles for it, and we know that if you want to get the number of moles, it's basically going to be your mass divided by your molar mass. And if we have a look at the periodic table, chromium somewhere here, yes, so chromium has 52, I'll just write it, 52 grams per mole. Okay, so then I am going to then say I have the mass. They gave us the mass, which is 2 grams. Okay, and then we have the molar mass, which is 52. So what is that answer? And if we get it, I'm going to say 2 divided by 52. So that is 1 over 26. Okay, I'm going to keep it as 1 over 26, but we can round it off to 2 decimal places, which is going to be 0.04 mole of chromium 3 plus. Okay, so yeah, now what are we going to do? How does this help us? Okay, so again, like I said, I consulted, guys. I totally forgot. I don't know if you guys remember Avogadro's number. You know, I actually had a student I was tutoring, a varsity student. We actually revisited Avogadro's number, and I totally forgot about it. So thanks to my fellow physics tutor, Mlungisinkosi, I consulted him without him knowing. And I remembered Avogadro's number. So this is Avogadro's constant. Let me just shift this side. Okay, so Avogadro's constant, basically, where we have in A, that's pretty much 6,02 times 10 to the power 23 particles per mole. Okay. And what we're going to do there, if we want to get the number of electrons, we're going to multiply this 6 times 6,02 times 10 to the 23 particles by the number of moles of chromium, so that we can see how much we actually have there. Okay. And once you do that, the mole will cancel out. Okay. And we're going to get the number of electrons, basically. Okay, so actually I should have said here number of electrons. Number of electrons. Okay, so once we get there, no, actually, yeah, I'm skipping a step here. We have the mole of chromium. I need to get the number of moles for the electron, because what I'm going to do here, I'm actually going to get the number of particles for chromium. I'm looking for the electrons, so there should actually be a step here. Okay, so I'm missing a step. So this is step 1, there's step 2, and then we're going to get to step 3. So we're not going to use the mole of chromium, we're going to use the mole of electrons. Okay, so we have 0,04 mole of chromium 3 plus. Okay, and then I want to know, looking at my formula here that we wrote down, remember this formula? So I have 1 mole for chromium 3 plus, and then I have 3 mole for the electron. Okay, so let us see what we can do with that. So I have 1 mole for chromium 3 plus, and I have 3 moles for the electron. Okay, so I'm going to multiply the 0,04 times 3, and at least I haven't gotten rid of that value. So we multiply times 3. I have 3 over 26, which is basically equal to, no, the previous one, 3 over 26, which is equal to 0,12 mole of the electron. So now for me to get the number of electrons, I'm going to take Avogadro's number, which is particles per mole. You could say electrons per mole, protons per mole, but we're interested in electrons per mole. Okay, so with that being said, we're then going to multiply by 0,12 mole of electrons. Okay, so we're going to take this value multiplied by 6,02 times 10 to the power 23, and that would be 2,08 times 10 to the power 23 electrons. Great, now we are getting somewhere. Okay, so I did above put it there that the charge then that they're looking for would be the number of electrons multiplied by the charge of the electron. Okay, and since we're looking for, I'm just going to go back to the question. Let me just minimize this. Okay, they want the total charge transferred when the mass of pure chromium changes by 2. And you might ask, why are we looking for the charge of the electron? Look again at your, did I draw it out? No, I didn't. Okay, if you look again at your electrochemical cell, if you look at your electrochemical cell, okay, at the anode, that is where oxidation occurs. Okay, so you have your battery source, power source, and there you have your ring. Okay, then you have your electrolyte there. Sorry, yeah, electrolyte. Okay, so here, that is your anode and that is your cathode, this side. So electrons are busy moving from the anode going all the way to the cathode. So they say the total charge transferred, you're gonna have to deal with electrons here. You can't deal with chromium ions. You're dealing with electrons, and that is why our focus is around electrons. Okay, I hope you understand. If it was something within the electrolyte, like the solution, chromium ions, then yes, we would go and look for chromium ions stuff. But here we're dealing with electrons when you talk about charge. So we have our number of electrons, which is 2,08 times 10 to the power 23. And we have the charge of an electron, so just in case you forgot, it's there. It's negative 1,6 times 10 to the power 19 or minus 19. Okay, so your answer here, because it's charged, you're going to end up with Coulomb. And I'm not really including the negative sign there. Okay, I don't think it's important. Yeah, you can include it. You can't. I don't know how the marking arrangement is going to be, but I'm not going to include the polarity of it. Okay. Oh snap, what did I do now? Okay, I'm looking for the calculator. So we have the number of electrons, and I'm going to multiply it by the charge, which is 1,6 times 10 to the power negative 19. And then we have 33,341,54 Coulomb. Okay, so that is the charge there. Or you could have simplified it and said 33,34 times 10 to the power 3 Coulomb. Same thing. Okay, and guys, that brings us to the end of the paper. I'm really hoping that you guys have learned something here. The learning never finishes. I'm also still learning, and I'm enjoying it. So I hope you guys are also enjoying it too. Please don't forget to like our videos, to subscribe to our channel, and please share the word with those who will be in grade 12 next year, whether upgrading or just, normal grade 12. This will come in very handy. So yeah, thank you very much and enjoy the rest of your day.